Hello, everyone, and thank you for inviting me to give this talk on our recent work called GECO, Geometrically Consistent Embeddings with Lightspeed Inference. So in this work, we propose a novel method for visual feature learning. And the second part is we also introduce an evaluation protocol that focuses on geometrical challenges like symmetries and occlusions. So basically, in recent years, wide attention has been devoted to the vision foundation models like DynaV2, as we all know. These models have seen billions of images, and yes, they show a terrific understanding of the objects in the wild, especially semantic knowledge. However, recent studies and as well our study suggests that they lack a proper geometric understanding, and they basically do not natively incorporate the 3D understanding in their representation of the world. So that's why previous work also tried to solve this problem. However, they are dramatically slow, so they take several seconds to process only a single image, which is basically because they also use image diffusion backbones. So while the previous work basically when we look at the segmentation results here. So for example, here on the left, we can see the ground truth segmentation of an unseen sample. And on the right, we see the segmentation results from a linear classifier from DynaV2 and previous work. So while DynaV2 is not able to basically separate left from right eyes, we can see that the competitor correctly distinguishes the eyes, but it requires significantly more computational resources, like 2 seconds roughly, as well as a lot of memory. So the impact of these limitations also becomes evident in downstream applications such as the correspondence estimation. So in this task, given a source image in a set of query points, the goal is to identify the corresponding keypoints in the target image. So basically, what we can see here, is that when objects undergo the non-linear transformations, like varying cat poses, partial occlusions and disocclusions can occur, and it's very likely that they occur. And here, for example, DynaV2 is not able to assign the ears and the pawns correctly. So they are assigned to their symmetrical counterparts. So to overcome these limitations, we propose a novel optimal transport-based learning approach that improves the feature quality, and so also the PCK scores and the image matching task. So our method maintains fast inference comparable to the original DynaV2 model. And the second part of our work is basically we identify the PCK limitations in measuring geometric-based performance and propose more detailed analysis of the metric along with a new evaluation protocol. So, okay, now let's start with the training strategy. So given 2 images, we consider their local image patches, and we pass them basically through the frozen DynaV2 feature extractor and trainable learnable LoRa module. So the LoRa module is here actually the only trainable part of our method. So after extracting the features, basically we pass them, we compute the cosine similarity matrix between all the patches. And this basically gives us this large dense matrix. And here, for illustration purposes, we just restrict our discussion to a few patches. So here you can see left and right eyes, back, nose, and background. So this is basically, we consider this basically as an input then to our optimal transport assignment, because this assignment is not ideal yet. So in order to pass it to the optimal transport, we also want to include the bin, which is here visible. So we allow also assignment to the bin. And this is basically the input, the score matrix input to our optimal transport problem. And the optimal transport is differentiable, is a differentiable synchrone algorithm, so an approximation of the ideal solution, which is differentiable. And then we get basically the optimized assignment here. So this assignment then provides the signal, or that's basically what we can basically use for backpropagation, because we then basically have annotated keypoint pairs. So we know where an assignment is correct and where it is not at the keypoint locations that are annotated. So we have basically three parts in our loss function. So it's a cross entropy loss. So we compare basically to the ground truth assignment at the locations of the keypoint matches. And we can say that if we have a incorrect assignment, like for example here the left and the right eyes are incorrectly assigned, we basically push down the assignment by this negative part of the loss function. Whereas we pull up the assignment at corrections that we know are correct. So the back should not be visible in the second image, or is not visible in the second image in the target. That's why basically we know that the back should be assigned to the bin. And we know this location. That's why we basically enforce a higher assignment here. As well as for the correct assignments, like nose is assigned to a nose, this is also correct. Whereas if the left is assigned to the right, this is incorrect, and we push it down. And note that also while pulling up the bin assignment, we also push down at the same time the whole row. Okay, so I will just briefly take a moment to explain the advantage of using optimal transport in a little bit more detail. So, okay, let's first look at an argmax assignment. So the competitor, for example, uses the soft argmax, which is closely related to this. So we can either assign the closest key point from source to target or from target to source image, which is basically a row or column-wise assignment. So we see here that the only learning signal we get from this is basically from the key points that are visible in both images. So only that is actually annotated. In contrast, if we use the optimal transport with the bin extension, we can also use the information about occluded objects visible in only one of the two images. In this example, we can assign the left eye to the bin as well as the right eye, because we know it's not visible in the respective other view. So basically, we know this and we can use it as a signal for learning. So now let me also quickly explain to you how we formulate the optimal transfer without learnable parameters. Okay, we first define the shape mass S. Is the mass of the shape. So with how much, we basically give the shape as a mass. And then we let the background, which has a mass 1 minus S, be assigned to the background. So here 1 minus S is basically the background. For the shape itself, we estimate the portion of the visible surface. So we estimate that here 0.5 of the shape is visible, and here 0.2. And the remaining one should be not visible, so that's in the bin then. So these marginal distributions are then basically the input to our optimal transport problem. So we pass this to the optimal transport, which is an arrow here, and we get an assignment, an improved assignment. And the improved assignment basically has can then basically use the marginals and say, okay, 1 minus S has to be assigned to 1 minus S, and it's more likely that then this assignment gets 1 minus S. And here also we basically have the prior knowledge that here at least 0.3 has to be assigned to the bin, because we know that 0.5 is visible here and 0.2 is visible there. So 0.3 has to go to the bin anyway. So we know, yeah, we basically give already some hint on finding this assignment via using the modules. Okay, so this is basically the setup of the loss function. So let's look at the figure from before again. So we finished now explaining the training loss, which is the optimal transport solver, which the optimal transport solver is part of. So we now use only the first part, the lower fine-tuned features for testing. Images can be processed individually. So our method is a feature extractor rather than a matcher. So this is important to also know in order to separate it from all the matchers that are out there. Okay, so for the first evaluation, we evaluate the PCK. So we have a query and check for where in the target image we get the highest attention scores. So the similarity is much better concentrated for us, our method. And so here we see that also the symmetric counterpart is visible, and we want attention also only to be here at the correct location. So here in the second example, we have a query which is then basically not visible anymore in the second view. And only the symmetric counterpart is visible. So we want low similarity on the whole image. So basically our method basically correctly assigns the symmetric counterpart to the bin, which then also enforces the low similarity of the features, which we can see here. And additionally, our approach is significantly more efficient, requiring 100 times fewer resources than the GEO baseline, while being both faster and more compact. Okay, so we can see that our method performance is better in 2 out of 3 data sets. And moreover, our model remains close to the original DynoV2 performance on the generalization dataset. So while the competitor Geo shows here this performance drop, it relies on the DynoV2 features as well as on the diffusion features, and still it can not maintain the performance of the DynoV2 model. So now let's check about whether the PCK has some problems in the evaluation protocol. So we differentiate here between the cases where we have a query that is visible in the target, but the symmetric counterpart is not visible. So this is quite an easy task, because then only one location can be correct if we want to test for geometric knowledge. So here in this example, it's much more difficult to find the correct location, because the ground truth and the symmetric counterpart are both visible. So the portion of these, we call it N11 cases, varies a lot across the data set. So this is the CUP data set here, and this is the SPARE data set. So it varies a lot how much of these cases we actually have in the data set. So the problem is that PCK is basically a black box. It measures the performance without discriminating between semantic and geometric knowledge. That's why we propose to break PCK into three parts. The key points were either the geometric counterpart is not visible in the target, or they don't have a counterpart in to be confused with. And the other part are those that have a symmetric counterpart visible in the target. Okay, so that was what we've seen already. So this is basically the breakdown into the two sets. However, during our study, we also noticed that the PCK's nature may hide ambiguous predictions. So, for example, consider this example. The ground truth position of the left eye and its geometric counterpart, the right eye, appear quite close here. So we discriminate three cases. When the prediction is close to the correct position, but far from the symmetric mate, we consider it as a clearly correct prediction. So this is this part here. Similarly, when the prediction falls near the wrong one, but far from the right position, this is a clear mislabel. But then also we have also the prediction where the prediction falls into the middle. So should we consider this prediction as correct now? The outcome actually should be regarded as ambiguous. So the N11 metric and also the PCK counts ambiguous cases, while it is actually while the clearly wrong prediction is not quantified at all. So we basically split up the N11 matrix and count the percentage of an unambiguous correct cases. So we have to split up here into the three sets again. And looking at the APK results, our method's performance is mainly, like the better performance is mainly motivated by much more clearly correct predictions. So notice also that we have less clearly wrong predictions than the competitor, while ambiguous cases remain stable. This indicates that the features learned by our method are more geometrically. And that's basically the number we have to look at. Okay, so here this is also another plot where we are varying basically the radius, and that's also one hyperparameter of the evaluation protocol. Of course, if the radius is getting higher, then we basically get fewer unambiguous correct prediction. And if we have a smaller radius, then it's basically getting lesser. So yeah, we can see this over all the different methods. And our method outperforms basically Geo in two of the three data sets. So it's independent of the radius. So our method basically outperforms the baselines that run in comparable time and performs on par more or less with the methods that require 100 times more resources. So now let's have a look at a different evaluation protocol, which basically segments the image densely using the output features from our model per image. So we've seen already this evaluation. As shown in the motivation, previous methods have been either slow or not correctly segmenting the feature space. We can already observe visually that our features can be separated by a linear classifier, as well as the competitor's one. So when looking at the confusion matrix between ground truth and predicted labels, we basically see, and when evaluating the mean IOU and the accuracy for the overall segmentation performance, we see that there's only a minimal performance drop by our method compared to the DynaV2, whereas this performance drop is more pronounced for the competitor. However, we can clearly see the checkerboard pattern when using the DynaV2 features for segmentation. So this is especially pronounced in the geometric subset of the features. So the confusion vanishes for the trained features. And we can see that this confusion vanishes also by looking at the metrics that focus only on the geometric part. So in total, we conclude that our features learn the geometric distinction, while this is quite similar to the competitor, while we better keep the overall segmentation performance. Okay, so in conclusion, we propose a method for a novel method for visual feature learning based on abnormal transport soft assignment. And we achieved the state of the art on multiple data sets while being 100 times faster and smaller than the competitors. So we developed this deep analysis and highlight how PCK, while useful, might hide geometrical understanding, and we propose an alternative solutions. So we release our code and implementation, which we believe will be useful to foster analysis for geometric awareness in visual feature learning and all related downstream tasks. So thank you very much for watching. And in case you have any questions or are just interested in the topic, please don't hesitate to contact me. Here's also the link to our project webpage. And yeah, thank you very much.